Right, so hello and welcome to this experiment in glider electronics. It's lockdown, my hair is getting awfully long and I've got a bit bored and wanted to do some experiments. So I'm going to do some experiments sort of tackling those slightly more difficult topics of electronics, things like electrical crosstalk and stuff like that. And today what I want to do an experiment on is I just want to demo electrical crosstalk. I want to show an actual situation where you can get electrical crosstalk, and I want to show on the oscilloscope exactly what electrical crosstalk looks like. Now, I'm really trying to make these so that even if you don't know anything about electronics, you should be able to follow and understand it. Let me know how I'm doing on that. A big disclaimer. I'm showing some very, very niche bits of electronics here. If you're not qualified to go and mess with glider electronics, then please don't. Best case scenario is you're going to nuclear electronics. Worst case scenario, you're going to end up with a fireball in your cockpit when you're flying, so don't do that. Secondly, if you are qualified to do glider electronics, I am not a glider electronics inspector. So nothing in these videos am I trying to make recommendations as to what you should do. These are experiments. I'm demoing stuff happening. They're presented as is. I try and talk through everything, but all sorts of things could be wrong with this. And so if you are qualified to do glider electronics and you go and do something, everything is your responsibility to do appropriate due diligence to work out whether something you've seen here is right or not. I accept no liability for it. So with that said, on with the experiment. Electrical crosstalk. We've got here some cables, or more precisely cable pairs, because if a signal is going between two devices, there's always a pair of cables. Even if you think there isn't, there always is. And what we're going to do is have a signal going down one of these pair of cables, which is kind of the noisy aggressor cable. And we're going to have a signal going down the other pair of cables that is sort of this sensitive, weak signal that we can get electrical crosstalk interfering with. And the particular situation we're going to set up here is I've got a standard dynamic glider microphone. Note that different types of microphone work very differently. This is a dynamic microphone and therefore has a particularly weak signal, which I'll come to in a moment, but other microphones are different. What we're going to do is feed the input from this microphone down its kind of shielded cable round here, and then we're going to, as if in your glider, you just put some, rather than having a proper shielded cable, you just put some gash cables here. It's going to travel from the shielded cable from the microphone down these gash cables. These little black things on the desk are just connector blocks into this connector block here, and then into this older Becker radio. So this is a Becker radio of the type that we've all just had to, well, in Europe anyway, I've just had to remove from our gliders so that we can have the smaller band spacing radios. Now, the reason I'm doing this with a real microphone and a real radio is because how much electrical noise you can pick up in a signal is all dependent on what's driving the signal and what's receiving it. There's certainly a lot that a receiving device can do to try to reduce the amount of noise that's picked up in the signal. So therefore, I'm not going to just be measuring the signal at the end of this cable. What I've actually done is strip this radio down and put in, this is an oscilloscope probe here, put an oscilloscope probe into the radio just after its input amplifier. So it's got an amplifier that does various things to make sure the noise is as good as possible. And I've just put the probe tip on the output of that amplifier. So what we're actually seeing is exactly what that radio is receiving, and therefore exactly what's going to be going out on your radio transmissions if you're talking on the radio. Right, so let's just talk about the other end here actually. This is a dynamic microphone. Dynamic microphone works by the pressure of the sound waves from your voice hit a diaphragm in the microphone. The diaphragm moves. There's a coil on the diaphragm, and the coil moves in a fixed magnetic field. Now, a coil moving in a magnetic field generates a voltage. So just from the energy from your voice hitting that diaphragm, a little voltage gets created, which really isn't capable of sort of like generating much power, much current down the line. So this is a tiny, weak signal, and there's no electronics in this microphone at all. So it goes all the way down this cable and all the way down these wires, all the way into that radio as just this tiny signal. And what we're talking about is sort of a 10 millivolt signal, 10, 12 millivolt. So standard glider battery, which we've got connected up to this radio here, 12 volts. 12 millivolts here. So this is 1,000th of the size of the voltages coming out of your battery. So if I talk in this, we've got a tiny, tiny little signal going down here and having to go into the amplifier here. And so that's going to be probably quite easy to get electrical noise into. So that's the signal that we're going to receive noise on. Now we've got to have an aggressive signal that's going to produce some noise. So what I'm doing there is I am simulating a GPS talking to a moving map. Now, in general in gliders, they use a quite horrible electrical signal called RS-232. I really wish they wouldn't use that in gliders, but they do. And lots of different devices talk with this in gliders. Some modern avionics is using other stuff like CAN bus now, which is a much better thing to use. But this really is quite a brutal, horrible protocol, or electrical standard end protocol, that is quite likely to produce quite a lot of noise. Now, in your manuals, it'll probably be referred to as serial, which is a bit of a wrong word to use because pretty much everything communicating with everything nowadays is serial. So anything labeled serial is probably RS-232, and that has quite a good chance of producing quite a lot of noise in your glider. Now, in this simulation here, I've got a computer down behind the camera that is coming to this connector here. So the computer has an RS-232 port on it. I can spit out data onto this plug here. That's literally going to be exactly the same as a real GPS unit. There's going to be no differences there. And on the moving map end, these are the oscilloscope probes that are wired into the oscilloscope. I've literally just got a 4,700 ohm resistor. Now that's what the RS-232 specification says a device should look like to the signal travelling down these wires. So although I haven't got a moving map here, that resistor is a perfectly good simulation of the moving map device, because all we care about is how much sort of current flows in these wires. Now, what is travelling down those wires? An RS-232 signal is made up of two things. Firstly, there's a signal wire, this one here, and that's sort of a square wave where the highs and lows in this signal, these are the binary data bits in the signal being transmitted along this wire. So it might be the latitudes or longitudes that are coming out of the GPS, becoming a square wave, and going to the moving map. Okay, so that's the square wave, but all electrical circuits are a circuit. If you've got a battery and a light bulb, you need a wire going from the top of the battery to one side of the light bulb, and then from the bottom of the light bulb to the other side of the battery. Otherwise, the light bulb doesn't light. A signal going between devices in a glider is exactly the same. The current has to flow around a complete loop. So the other wire in an RS-232 circuit, and this is one reason why it's not a very good type of signal, is a ground. It's much better if the other signal is not a ground, but in RS-232 it's a ground. And you might think, well, that's a ground, that's just connecting the two devices together. Well, if you stick a current down one of these wires, it's got to go through this resistor and it's got to come back down the other wire. So although this wire is ground, it's still carrying the current of the signal. So the pulses of digital data coming down here are essentially going to be a varying current. It's going to be a current that changes every time that signal goes high or low. So we've got a varying current going down here. It goes through this resistor at this end, and it comes back down here and goes back to the device that produced it. So what we've got here basically is an alternating current flowing through a loop of wire. And this loop of wire looks very much like a sort of a circular antenna that you might have had on your TV in the old days. So this is basically an antenna with an alternating current. So this is going to be producing an electromagnetic field out of it as the current varies. And that's going to intersect with this other aerial over here. And an alternating current going into an aerial is going to produce variations in the voltage in this signal. And broadly, what I'm now expecting to happen, because this is a pretty high current brutal signal, and this is a very weak signal, is we should end up seeing this interfere with that if we look at what's coming into this radio. So let's, that's the plan. Let's simply look at what this radio is actually hearing without talking about this yet. We'll come to this in a second. We're just going to look at that one. So over here I've got an oscilloscope. One of its probes is in this radio looking just after the input amplifier. The other one is looking at the end of this RS-232 line. We'll come to that one in a second. If I put the display that I'm just recording off the oscilloscope, if I put it up here, what you're now seeing on the screen is what that radio is currently listening to from this microphone. And the peaks you're currently seeing on the wave are just me talking here. If I come closer and start talking, you can clearly see my voice is getting picked up by this microphone. So that's what a wave looks like once it's got into the radio. Now, we're asking the question, how much interference can we create? So if we take this other signal, this RS-232 signal, and as I say, these wires, this is not how you'd wire up a microphone. This is, you've wired it up really horribly, and I'm really trying to create a worst case situation here. But let's say you've wired up a microphone with these two cables, and the little coil in this is producing a voltage difference across these two cables that is picking up. Now you bundle it all together to go through some bulkhead or something like that, or through the hinge in your canopy. And so you're taking those two aerials and you're like scrunching them all together in the worst possible way you possibly can. This probably isn't going to be good. So we've done that. We've now got a little bit of cable run where those two loops of signal are joined together and their aerials are nice and close together and they're going to be coupling horribly. So if we look on the oscilloscope, if we look at my voice just on this microphone, I think I'm a reasonable distance away from the microphone as I would be in a glider, and we can see the size of the signal on there that this is therefore creating. Now if I dump a whole load, so at the moment there's no data flowing on this cable. If I click on this mouse button here, I can dump a whole load of data down that signal. So this is what happens. I'm just going to speak at a sort of a fairly consistent level, just so you can see the level of my voice on the oscilloscope. And if at the same time I dump some data in, you can see that there's now a noise of data there, with my voice just poking up either side of it. Hopefully the data will stop. So again, now we've gone down to a baseline level of noise when I'm not talking. And we can see that broadly, if I put my fingers on the scope here, broadly we've got a signal sort of this big when I'm talking. And now if I stop talking and just inject signal down this RS-232 line, you can see now that there is the noise, okay? And it's pretty much swamping out my voice. If I'm talking there and I inject the noise, you can see the noise floor comes right up and you can hardly see any of my voice anymore. So to me, there is nothing concocted in this experiment, basically. I really am reading what the radio is seeing. And this is a perfectly reasonable RS-232 signal. Now, I've got, like, the worst case was, but I've seen this in gliders. And literally, if you suddenly stuck a signal down those RS-232 lines, it swamps my voice out on the oscilloscope there. So that really is not going to be a particularly good situation. So let's now have a little bit of a look at what this noise actually looks like, because we've seen, this is on the screen at the moment, we've got what the radio is picking up, and we've seen that when I inject a signal into here, that basically we get a huge amount of noise coming out on the radio signal. But what do these two signals actually look like in detail? If I turn on now the other signal onto this oscilloscope and just separate these out a little bit, what we've now got is, at the moment, this yellow line here is the RS-232 signal, and there's no data being transmitted. If I just press and hold a key on this keyboard, I can send individual key presses down that line, okay? So you can see here, when I press a key, we get spikes on this RS-232 line. And if I zoom in, and I've got my finger held on a key, so it's continuously sending key presses, we can see that an individual key press is a bunch of binary data. If I press different keys, we get different binary data here. I'll just put this on triggering so that it doesn't. Okay, so it's now, it'll only show stuff when there's stuff going down the link now. If I press different keys, here's the key 1, and this sort of drop here is a binary 1. That's now binary 2. As I press the key 2, as I press the key 3, we now get a count of binary 3, binary 4, binary 5, binary 6, binary 7. This is basically counting in binary as I press the number keys. So none of that's particularly important, but what we've got is a digital signal that is dependent on what character we put down this digital link. And I can stuff a whole bunch of data down using the mouse. If I, instead of single keys, if I blast a whole load down, we get a digital signal that kind of looks like this. So you can see there's a whole load of complex digital data going down there. But that's the RS-232 signal. Let's have a look at what's happening in this radio. What we can see here, if we zoom in on this signal a bit, is that here's the signal when we haven't really, when we've got no digital data going down here, and it's not too noisy. But if we look at this bit where we've got some digital data, what we can see here is every time we get a transition in the digital signal, we get a spike coming out in the output signal. Now it goes back to this middle level again, but basically it's the transitions, because electromagnetic transference between two signals, just like in a transformer, only works when you've got a changing current and changing magnetic field. So as the current changes in this input signal, or in this RS-232 signal here, we get a spike on this edge, we get a spike upwards inside the radio, and on this edge here, we get a spike downwards inside the radio. And that's exactly what the coupling actually looks like when it's actually occurring. And it's these spikes here just coming from the transition. So it's only when we've got the transitions that we get the spikes coming out. It's those that are swamping my voice out. Okay, so there's me speaking just on top of, you can see, there's me pressing a key continuously. You can see the spikes coming out on the bottom here, and you can see my voice talking into the microphone around it. And you can see that the magnitudes of these noise spikes here are fairly similar to the magnitude of this overlaid waveform from my voice. So there's noise, or electrical crosstalk. There's lots of other types of noise. I hope that was sort of interesting and informative. Next time what I'm going to do is stop being really silly and using just completely untwisted, unshielded cables. And I'm going to see what difference it makes if I swap some of these cables out with twisted cables or with shielded cables, and how much that reduces the actual noise level that we're picking up in this system. So that'll come next time. If you're a member of YouTube, then feel free to like and subscribe. Contact details on the screen if you want to get in contact with me for anything. And thank you very much. See you next time. Thank you.